How's everybody doing today? I hope everybody's doing well and feels strong to learn a lot today.
Stronger than hydrochloric acid.
That's good. Awesome. Awesome. We need to beat this COVID and this situation. Awesome. So today we are going to experience and to investigate the sixth experiment in Labflow, which is the Le Chatelier principle. Last week, when we studied the experiment determination of the equilibrium constant, we talked about some reactions that never end, which means reactions that do not stop when one of the reactants is consumed. Those reactions, we said last week, are called reversible reactions. And those reactions that we said last week at some point reach a state of equilibrium. And what does that mean, to reach a state of equilibrium? That the rate of the forward reaction equals the rate of the reverse reaction. And when the system is at equilibrium, the concentration of the reactants and the products do not change. Today, in the experiment of Le Chatelier, we are going to investigate what happens with systems at equilibrium when we disturb the system. What do I mean when I say disturb the system? We can disturb a system in equilibrium in many ways. We can add more product, we can add more reactant, we can add heat, put it in a water bath and raise the temperature, or we can remove heat, or if we are talking about a gaseous system, we can add an inert gas, or we can change the pressure by changing the volume of the container. So there are many ways to disturb a system in equilibrium. And what does the Le Chatelier principle say? It applies to systems in equilibrium. And Le Chatelier said that when we have a system at equilibrium and we disturb the system will shift in the direction to minimize that stress. In other words, a system at equilibrium tends to maintain at equilibrium. And they're not in a chemical reaction at equilibrium. There are not many ways it can shift. A chemical reaction can shift either towards the product or either towards the reactants. So in today's experiment, we will have two different systems, two different chemical reactions that are at equilibrium. And we are going to add or disturb the system, both systems, in different ways. We are going to disturb the system by adding more reactant or placing the tube in a water bath or in an ice bath. So this is basically the objectives of today's experiment. Basically, to examine and verify the Le Chatelier principle. So as we do each week, I will give you a quick overview of the experiment. Then we will do a learning check. We will go over many possible ways of disturbing a system equilibrium, and we will learn what is the response. And then towards the end, we will go over the questions in the report, but by then you will know all the answers. But we'll review and make sure you have all the concepts to get an A in your report. So let's get started by sharing the page of the experiment. So we said here in the introduction, we had a little bit of this last week when we studied the equilibrium constant. We mentioned, basically we said that here, the equilibrium reactions, let me see if I can write. Here we have an reversible reaction. We said that they are indicated with a double arrow to show that it doesn't have an end. It's a continuous dynamic state. But the concentration, we said, do not change because the rate of producing the reactant is the same rate of the reactant disappearing. And then we saw that in a reversible system, we have an equilibrium constant that is expressed as the equilibrium ratio of the products to the reactants raised to the coefficient in the balanced equation. All this we saw last week. But when the reaction, let's say, have a reaction in equilibrium, and we add more A, more product, then the reaction initially is not at equilibrium. When any reaction is not at equilibrium, we use this expression. We use the quotient, the Q. I don't know if I'm pronouncing it right, quotient expression. The quotient expression is exactly, if you compare with the K, if you compare these two expressions, is the same. But what is the only difference between these two expressions? Is that in K, in the equilibrium constant, we use equilibrium concentrations. That's why here it says equilibrium. But if I disturb the system in any way, I won't have a system in equilibrium initially. So I need to use this QC that has the same expression, but the concentration are not going to be the same because I did initially. Once the system reaches the equilibrium, the QC equals the equilibrium constant. And then the value of the equilibrium constant will not change with time. Just as a refresher, the equilibrium constant, the K, only changes with temperature. So we can predict in which direction the reaction will proceed when we disturb the system. And that is all about this experiment. Suppose, let's say here, let's look at this reaction, this blue, A plus B. Suppose that I add more A. I have a system. Le Chatelier principle applies only to systems at equilibrium. So I have a system at equilibrium, and I decided I'm going to disturb the system, and I will add more reactant A. When I calculated the Q Look at the expression here of the Q. Where is A? Because I added A, I will have more, a bigger number. The concentration of A initially is higher. Then, because the concentration of A is higher, I want you to tell me how is going to be the value of QC here when I add more A. Look at A. A is in the denominator. Exactly. Thank you, Alonso. Awesome. Alonso says that the value of Q decreases. And that is totally correct. Because, why? Because if I have, let's say, I add A. When I have a fraction, if I have 4 divided by 4 equals 1, right? But if I have in the denominator down a bigger number, like in my case, because I add A, and here I have a bigger number, let's say I have 8, the answer is a smaller number. It's going to be half instead of 1. So the value of this fraction decreases. And then we can predict in which direction is going to move the reaction. When QC is smaller than the equilibrium constant, Le Chatelier said that the system tends to be at equilibrium. The system tries to go to equilibrium. So what is going to do? The only thing the QC have the same value of Kc is A smaller and the products bigger. Right? Does it make sense so far? Since Kc does not change, has a fixed value, we said the equilibrium constant does not change. It's tabulated in books at different temperature. So Qc is smaller than K. The only way for Qc to equal the value of Kc is to increase the product's concentrations, to increase the value of C and D until QC equals Kc. So the reaction will move in the forward direction. Does it make sense? So basically the effect, to make it a summary, of adding a reactant to an equilibrium mixture is to force the reaction to move in the forward direction. We are going to see more examples, but any questions so far? Okay.
Oh, sorry, I have a question.
Yes.
When a reaction is at equilibrium, do the amounts of each reactant and each product, stay the same? Like if you added another A, it changes the equilibrium, but if you don't add anything, will it remain equilibrium?
Right. If the system is an equilibrium, while the system is at equilibrium, there are see here there is concentration of C has a specific concentration of C at equilibrium. The concentration of C is different than D at equilibrium, but they will not change. It will be constant because at equilibrium, why the concentrations are not changing? This is interesting because we say that an equilibrium is a dynamic state, right? What does that mean? When I say it does not end, means that the rate of the production of C is the same rate as the disappearing of C. That's why the net result is that the concentration of the reactants and products at equilibrium don't change. I don't know if that's the question that did I answer your question? Okay, awesome. So once we disturb the system, okay, then we don't have a K anymore. The concentration are not the concentration of equilibrium, and we need to work with QC and then we calculate the QC, and we are going to find out, because Le Chatelier said that it's going to shift toward the direction that minimizes the stress. But we will go over every change of any different disturbances. But this is just the beginning. So this is one way of disturbing. We said that adding a reactant at an equilibrium mix is to force the reaction to move it in the forward direction. And let's say what happens when we change the temperature. So here there is a summary, but you don't have to memorize it. That is what we just seen. If QC is smaller than KC, the reaction moves in the forward direction to reach equilibrium. And then the opposite happens if QC is higher than KC. And then they are talking here about the temperature. Suppose you change the temperature of a reaction that is in equilibrium. The reaction will react. The system will react in a different way depending on if the reaction is exothermic or endothermic. Everybody remembers what is exothermic and endothermic. Let's say I have a reaction A plus B produces C plus heat. We can treat the heat as a product or a reactant. What kind of reaction I have here? Exothermic or endothermic? Exothermic, thank you. Yes, that is correct. Some people remember it like exothermic, they remember exit. Exo and exit. So people remember that the heat exit system. Why exit? Because it's on the product side. You start with A and B, and you end up with heat. It releases heat to the surroundings. With heat as a product is exothermic, but with heat as a reactant is endothermic. Thank you, Michael. That's correct. We always view it from the point of the solution, correct? Yes, awesome. We always, because in physics is different. You are right, Michael. Exactly. We look at the system. We look at the system and we said, okay, the heat leaves the system. Then we say that it's exothermic because it exits the system. And also, when you look at here, okay, it's in the next page, the enthalpy or the heat of the reaction is going to be lower than 1, negative or positive. all the exothermic reactions, if you remember, are negative. Why? Because as Michael said, this is always viewed from the point of the system. So the system is selfish. I'll always remember that as, okay, the system is selfish. So everything that the system gains, either heat or work, is positive. And everything that the system loses, everything that is a loss, like heat or work, is negative. That's why the delta H is negative. That's how I remember. That is a selfish system. If it gains, or if it's on the reactant side, on this side, it's going to be positive. If it loses, it's negative. Okay, so we said that this reaction is exothermic. And now we are trying to see what happens if we add heat or if we remove heat. That's another way of disturb a system in equilibrium. So we have here an exothermic reaction. When we add heat, let's say we add more heat. I want to disturb it. Let's say we are resting in a couch and somebody comes and disturbs us, wake us up. Okay, we don't want to leave the system at equilibrium. We heat the system, we put it in a water bath and raise the temperature. The system will try, according to Le Chatelier principle, will try to remove the added heat by moving to the side without heat. Which one is the side of without heat? Obviously is this side, the reactant side, because we can write the heat as another product. So it's easier for us to figure it out. So Le Chatelier said that if we add more heat that is on the product side, the system will shift towards the side without the heat. So for exothermic reaction, it means moving towards the reactants A and B. But what happens if we remove heat? Let's say I remove heat. So if I add heat, it goes like that. But what happens if we remove heat? What is Le Chatelier saying? If we remove heat in an exothermic reaction, the system, because we are taking away that heat, the system will replace the removed heat by moving to the side with the heat. Which one is the side with the heat? The product. So the system will shift toward the product in an exothermic reaction. Obviously, in an endothermic reaction, is going to be the opposite. Any questions so far? Exactly. Yes. Systems hate imbalance, same as us. Yes. When somebody disturbs us, we try to go back to equilibrium. That is correct. And that's a good way of remembering it. So here they are showing in this page how they write in exothermic reactions. The heat is on the product side. And in endothermic reaction, the heat is on the reactant side and is positive. We saw that. And then at the end of this overview of the experiment, basically they are showing us the two reactions that we are going to explore today. Since you are not in the lab, you are going to be given the observations, and you will need to say if the reaction moves towards the reactants or towards the products. So the first reaction is this reaction here. So reaction of iron 3 that reacts with thiocyanate to form this complex, iron thiocyanate. And that complex, this one, has an intense red color. So they also pick these systems because we'll know after disturbing the system if it shifted towards the products or towards the reactant because of the color. One side is red and the other side has almost no color. The thiocyanate has no color, and the iron plus 3 depends on the dilution, is a light yellow or no color. So you will know if you see a darker red, that means the reaction shift to the products, towards the products. So we'll study this reaction, and basically we change the reactants, and we'll do a series of reactions that we'll go over shortly. And the second reaction that we are going to study is this reaction here. When you look at the guide, I cross this because the charge of this complex, it's tetrachlorocobaltate 2 complex. And here, if you look at your right, write-up, it's I think 3+, and that is not correct. What is correct is what is written here. Cobalt, Cl4, and the whole charge is -2, because the cobalt is +2. The chloride is -1. So the whole thing has a charge of -2. But that's just not to the point. What does the alk stand of? Yes, the alk is very, very, very important in this reaction because it has different colors. It means alcohol. Basically, what you have is this complex, the tetrachloro, this one, the tetrachlorocobaltate in alcohol is blue. This has a blue color, but only has a blue. This is actually the picture that I send you when I send the email inviting you to this workshop. The picture down is showing 2 different test tubes. Okay, is this reaction. So when the cobalt chloride 4 -2 is in alcohol, it's going to be blue. As soon as you add here DI water, the color changes because this complex disappears, and this is the equilibrium reaction. And this one, instead of being blue, is going to be pink. That's why it's important. This complex has to be dissolved in alcohol. So the color changes from blue to pink after we add water. And the darker the blue color, the higher the concentration of the complex cobalt Cl4. Any questions so far of the quick overview of the experiment? Then we will go and do a learning check, and that's where we are going to go in detail all the cases of disturbing a system at equilibrium. Okay, let's look at the first question. What is an endothermic reaction? We already said that. How can I write an endothermic reaction? And you say, how does it feel on the outside? Because I think that's a question that we will need to answer somewhere in the quiz or somewhere. So what is endo? We said that exo is exit. That means it's on the product side. Endo, exactly. Thank you, Michael. That is totally correct. Exactly. When we have a reaction that is endothermic, we are going to have the heat on the reactant side. Now, how does it feel from the outside? Feels cool. Yes, because of awesome. Thank you. Yes, exactly. That a bit chilly. That is totally correct. Thank you. Exactly. When the system absorbs, it feels cold from the outside. Only the system releases, it feels hot. That is correct. Awesome. Let's look at the next question. What happens, and this is an important question. You will need this for lectures as well, actually. What happens if you add hydrogen gas to the following equilibrium? So let's pay attention a little bit to the reaction. First, we have to look at the phases. All the reactants, hydrogen is gaseous, nitrogen is gaseous, ammonia is gaseous. So we have a gaseous system. And then it says add hydrogen gas. I have to look, the first thing that I have to do is look if the gas that I'm adding is included in the reaction. If it's not included, perfect. Yes, Alonso. Yes, that is totally correct. If it's not included and the system is gaseous, it still affects the total pressure, and we'll go over that. But for now, all it happens is that I'm adding hydrogen. So the system is already in equilibrium. And when I add hydrogen, it disturbs the equilibrium. And having too much on the reactant side compared to the product side. So what is it? According to Le Chatelier, the system will shift to counteract the addition. Exactly. So would it matter if you added the nitrogen instead? No. Okay, so as I said before, it's too much, and the system will shift in order to counteract the disturbance. So we know what would be the answer. According to Le Chatelier, what happens? It's going to create more products. But here I have a few questions. Let me see. Let me read it. Okay. Okay, the reaction shifts to the right. That is correct. And then, so would it matter if you added the nitrogen instead? No, if I add nitrogen, it's still, because I'm adding too much of reactants, it's still is still shifting toward the products. And then we'll go about the pricing. It's just increasing the pressure for the reactants. Okay, that we are going now. We are going to the next question, and we are going to talk about pressure. But for now, if you add any reactant, it's going to shift to the product. If you add a product, it's going to shift to the reactant. So let's look at the next example. Suppose you have a container holding the formation of phosphorus Cl5 at equilibrium. So you have this reaction. This is, again, we are having a gaseous reaction. Everything is gas. So they are asking 3 questions. The first question, what is the impact in the system involving gases when you decrease the volume of the container? This is important. Decrease when you have a gaseous system. You can disturb the system by changing the overall pressure. Oh, exactly. I can read. Okay. Yes, you're right, Yola. So going back, you can change the overall pressure of the system by changing. There are 2 ways, actually, of changing the overall pressure of the system. You can either change the volume of the container. You have a container with all these gases, or you can add an inert gas. Let's say but we are going to talk about that in C, but that's okay. If you add a gas that is not involved in that chemical reaction, it still affects and disturbs the system. In our case, when we decrease the volume, what happens to the pressure? What happens to the pressure? The pressure increases. Yes, exactly. It's inverse. Thank you, Michael. So it says, when you decrease the volume, if somebody says decrease the volume and you have all gases, but you know when you press, the pressure is higher. So the pressure of the container increases for all the components. To reduce that stress, the equilibrium system, something you have to remember, will shift to the side with fewer total moles of gas. That's exactly what somebody says here. 2 people answered that. Thank you. Exactly. So that's something that you need to know. If you have a system like this and you increase the pressure, in which direction the system is going to shift? There are only 2 directions, right? Right, left. Which one is the correct one? And Le Chatelier says that it's going to move to the side with fewer total moles of gas. Right. The reactant side has 2 moles, one of these and one of these. And the product side has only 1. So increasing the overall pressure by changing to a smaller container shifts the equilibrium towards the product side. So the answer will be the right. Any questions so far? Let's go to the question B then. What is the impact of removing PCl5 from the equilibrium system? That you can tell me. Somebody said shift to the right? Why to the right? It's correct though. It's very good, but why to the right? It's correct. Because I'm saying removing. Yes, awesome. Thank you. Exactly. So the system will shift toward the products, as you correctly said it, to replace the removed product and reestablish equilibrium. Very good. And how about C? What is the impact of adding argon gas to the equilibrium system? And that is inert gases increase pressure. That is correct. The argon gas does not appear in the equilibrium, but the presence of argon changes the pressure, will increase the pressure in the container. So the system will shift to the side with fewer moles of gas. Exactly as before, when we increase the pressure, no matter if we add an inert gas or change the size of the container, doesn't matter. If the pressure increases, the system will shift to the side with fewer moles of gas. So again, the reactant side has 2 moles and the product has 1. So the system will shift towards the product side. Any questions so far? Then we're going to see the next problem. What is the impact of adding heat to the following reaction? Is this an endothermic or an exothermic reaction? Let's see what you think. Let's go with the first endothermic. Yes, exactly. Thank you. Very good. It's endo because the heat is on the reactant side. Exactly. And then it says, what happens if I add heat? Exactly. The reaction shifts right. Exactly. Very good. Awesome. This is all correct. So when we add heat, by increasing the temperature, you will put your test tube in a water bath. It's like adding a reactant because the reaction is endothermic. So the system will shift toward the product. And then what does that mean? There's going to be more ions in solution. It will increase the solubility of the salt because at the end of the day, this is a salt. Here it says S. So if we raise the temperature, the solubility increases. Let's look at the next question. What is the impact of adding hydrochloric acid to the following reaction? So this is the same reaction I had before. Here I have a question. It says, I understood K to remain constant, but Q will decrease with an increase in the denominator. I'm not sure. For question 4. Okay, let's go back to question 4. Okay, seems that, yes, exactly. The only way to change the equilibrium constant is by changing the temperature. Yes. Okay, so let's go back to the exercise 5. What is the impact of adding hydrochloric acid to the following reaction? So we have this reaction, right? And they're telling us consider the following reaction. And they are saying that the carbonate reacts with the acid to form carbon dioxide. So we didn't see these cases before. So far we saw what happens when we add heat, if it's exo, if it's endo. We saw what happens when we add any of the reactants. But in this case, they're telling me, oh, I'm adding hydrochloric acid. And I look at the main reaction here, and I said, hydrochloric acid is not written, is not participating in my reaction. But we are changing a chemical that is related to the chemicals in the reaction because it reacts with carbonates. So the hydrochloric acid, by reacting with carbonate, because they are giving this reaction, the carbonate concentration decreases. So this effect of adding hydrochloric acid is the same as removing carbonate, which means that the system will shift to the right. So every time you have a question that you see that they are adding a different reactant that is not involved specifically in the chemical reaction, you will be probably given a second reaction, and you will have to see how the second reaction changes the concentration of one of the reactants or the products. Does it make sense? Okay, so then we'll move to the next question. What is the impact of adding silver carbonate to the following reaction? Can you tell me what happens? Can somebody tell me? Thank you. Yes, no change. Awesome. Exactly. Remember, I'm saying what I'm adding. I'm adding silver carbonate. Silver carbonate is solid. Remember that pure solids and liquids do not appear in the equilibrium expression, and they do not factor in equilibrium shifts. That's why, so we only include gases and aqueous solution. Yes, exactly. Exactly. In the equilibrium constant, that is correct. Exactly. So if the system is at equilibrium and you change the amount of pure solid or liquid, it will not shift the system, even though the solid appears in the reaction. In this case, yes, the KSP, you will see it because I think it's coming later. The KSP, it doesn't involve the solid. The KSP of this is going to be concentration of silver square times concentration of carbonate. That's it. We don't include in the expression of the KSP, which is the constant of the solubility product, we don't include the solids. That's correct. And that's why it has no impact on the shifts? This was a tricky question, but you answered it. Any questions so far before we are going to take a look at the report? So let's go to the report then. The report, after you listen to me, is going to be easy peasy. Comparing to all the others that you did, it's gonna be you're gonna laugh, but still pay attention and get an A. This is your opportunity to raise your grade, because you don't want to mess up when you have an easy lab. So let's go over that. This is what you are going to see. You are going to see this. Because you are not doing the reaction in the lab, the color observations here are given. So let's go and look. What you have two different systems at equilibrium. This is what you are doing in the lab. The first one we saw is this reaction. Iron plus thiocyanate produces this complex that is red. And here Alonso is saying that the iodine clock reaction was the most difficult lab. Yes, and I thought the previous was difficult as well. Which was it? The colligative properties, the freezing point depression. But yes, both were, I think, hard. So this one, aim for an A, and we don't, sometimes we mess up in the easiest one, but no, we are not gonna do that. Okay, so let's look at what we have. We have 6 tubes. So we are going to do, to perform this reaction, we mix iron and thiocyanate, and then we have a system equilibrium. And we have 6 tubes with the same system at equilibrium. From tube 1 to tube 6 are all the same. The first one, the test 1, we are not going to disturb it because we want to see the color and we want to compare the tube 2 to 6 to the tube number 1 and compare the color. And because this, if the reaction shifts toward the reactants, it's going to have one color, and if it shifts toward the product, it's going to have a different color, then you will know in which direction the system shifts when you disturb the system. So let's look at the tube number 2. How are we disturbing the system? Add potassium cyanate. Is that a reactant or a product? It's a reactant. And because we are not in the lab and we don't need to observe, they are telling us that it's slightly darker red, slightly darker red. What does that mean? They are implying that the product, it shifts to the products because it's a little darker than the control sample that we had. When we add reactants, it shifts towards the products. Does it make sense? So you will have to say reaction response. In this case, is obvious towards the products. Does it make sense? Because they say they are telling everything. That's why I say it's so easy. How about the second one? Tube number 3. You add iron nitrate. Again, you are adding reactant. And they're saying it's darker red. So you figured it out. What is the response? Similar to previous one. Because if we add Exactly. Yes, Alonso. Exactly. That's correct. Now let's look at the tube number 4. They are saying that we add sodium fluoride. And we look at the reaction and we say, where is the sodium fluoride? No way. We don't have that. But I think they're telling us, if you read the procedure somewhere, we know that the iron +3 reacts this is a case that it reacts with iron. So basically, it's removing the iron from participating in making this complex. So when we are saying, and they are saying no color, even though if we don't analyze, as I'm showing you why, what does it mean no color? The left side is no color. The reactant side is no color. We said that iron has almost no color. It's a little yellow, and the other no color. Only the product side is. And if we add fluoride, it says no color. So you know where it shifts to. And now here you know why it's shifting in that direction, because it's like, basically, it's like removing iron. If you remove iron, because the fluor is reacting, no, it says, yes, exactly, that's correct. Yes. So if we remove, the system tries to replace the iron that it was removed. And then it says what happens when you put the system in a hot water bath. It says almost colorless. You know which side. And what happens if you put it in an ice bath? It says darker red, which means it goes, we know which side is red, right? Any questions so far? This is easy, just by the colors. Yes, definitely I can explain that away. Again, it's just yes, I can explain that. So they are asking you in which direction it shifts. So the hot water bath, it says when you put that system at equilibrium in an hot water bath, it says that the system changes the color and has almost no color. Which side has no color? The reactant side or the product side? Exactly, reactants. That's why the system shifts toward the reactants. This is your observation. And the opposite says in the ice bath, slightly darker. Which side in this reaction is slightly darker? The complex, the product side, right? Yes, awesome. That's why we say it shifts to the product side. Does it make sense? Okay, good. Okay. Basically, Kevin, what you are doing is looking at the color. I think it's so simple that you probably think it should be more difficult. It's basically looking at the color. If you disturb the system and the system becomes intense red, darker red, you will say the system shifts to the product because the product has that color. But if you disturb the system and the system has no color, you know that the reactants have no color. So you will say the system shifts towards the reactant side. Basically, that's all what it is. And now let's, oh, thank you. So it's sometimes it's when it's very simple, we look that it should, we think it should be more difficult. And then in here, they're asking, for test tubes 2 to 6, explain how each change affected the equilibrium in terms on how each change affected the value of QC or KC and how this is consistent with your observation. So basically, we'll do one, and basically, let's go back here and let's do the number 2. Let's look at this. Basically, what you have to write is, when you add more reactant, the Q is becoming smaller. Everybody sees that? The Q becomes smaller. In this one. Why the Q becomes smaller? Because we know the expression of the Q, and we know that the reactants are on the denominator down. So if the what we saw at the beginning, so if the Q, when we add more reactant, becomes smaller, the concentration of the product needs to increase in order to reach equilibrium. So basically, here you said, okay, it shifts toward the product, right? So you said towards the product. Why you said that? Because you just look at the color and you say, okay, slightly darker. Okay, then it's the product. But now they want you to use the Q and try to use the Le Chatelier principle and see if it makes sense what Le Chatelier said. And yes, it does, because you are going to say that because when we add the reactant, when we add the cyanate, the potassium cyanate, then the Q becomes smaller, and the concentration, the only way of Q to equals the equilibrium constant is to raise the concentration of products. Does it make sense? And then it matches your observation, because you said, yes, you said that it's going to shift toward products. Any questions there? And you will have to answer that for 2, 3, 4, 5, and 6.
I have a question.
Yes.
So basically what you're saying is the darker the color gets, the more it will shift towards that side?
Right. The darker the color is, the higher the concentration of the product. But even though in tube 2 it's a slightly darker, well, that's enough to say that the concentration of the product is higher or increased. Yes, because all you are doing is having different colors. The reactant has one color and the product has a different color. So when you disturb the system, you look what is the color after you disturb the system. And that is from where you take your conclusions. Did I answer your question? Yeah.
One more. If it shifts towards the reactant side, is that because the concentration there is lower? Like if it has no color or almost no color, it's because the concentration there is really low?
If it shifts to if it shifts towards the reactants, means that you have almost no complex, almost no products. You disturb the system and you separate it, and the shift means that most of your product is as iron and thiocyanate. So basically, you won't have you won't have the color. You will see the color only when the iron and the thiocyanate bond and make that complex. If they bond, then you will see the red. If you don't see the red, means they separated. And that is what it means when the equilibrium shifts to the reactant side. Basically, you don't see the red because you have everything, almost everything, as iron and thiocyanate. Until, of course, is going to recover and try to reach equilibrium again. Does it make sense? Kind of, I will walk. Okay, no problem. I'll stay. Please repeat the test tube 3. I think it will make much more sense with the two comparison. Sure. Let's look at test tube 3. Test tube 3 is basically the same as test tube 2. Because what are we adding? When we look at the reaction here, we are adding, again, more reactant. And they are saying that when I add more reactant, we know, but because of the Le Chatelier principle, that the equilibrium will shift toward the right. And here they are saying darker red. What does it darker red? Means that the concentration of the product is higher. The darker the color, the higher the concentration of this, and the lower the concentration of iron and thiocyanate. So you can have the iron by itself in the solution and the thiocyan. If you have all these in a beaker separated, basically they form this red complex. But let's say they don't form, has no color. So if the color disappears, means they are not bonded. But as soon as they bond, you will see the red color. So in tube 3 is the same as before. You add, all you have to do in tube 3 is look at what they say. It's darker red. Okay, it's darker red. And then you say, who is the control tube is light red. So if it's the red is more intense, means the red is the color of the product. If the red is more intense, the concentration of the product is higher. Did I answer that question? I'll stay later and we can go over that as well. And then when we look at the Q, you're welcome. And when we look at the Q, let's look at the Q. What is the Q? The Q in this reaction is going to be the concentration, how we define the concentration of the product is exactly the expression of equilibrium, but the concentrations are not the equilibrium concentrations, are the concentration when we disturb the system. So as soon as we disturb the system, the Q is going to be the expression of the Q. So what they want us to do next is saying, does it make sense here? You said, okay, the reaction shifts toward the product as you see a darker red, and you know that the red is the color of the product. Now they are saying, tell me if it makes sense with Le Chatelier principle. And then we will have to do the Q. What is the expression of the Q? We are adding iron. So if we are adding iron here, the Q is going, because it's in the denominator, the Q is going to be smaller than the K. The only way of be equal to the K is by increasing the concentration of the product. So the reaction needs to shift towards the product. And also you can see when in the summary that says if Q is smaller than K, the reaction shifts towards the product. You will see that summary and you can read that again. Does it make sense? Okay, and then it says, based on your results from test tube 5 and 6, is the reaction exothermic or endothermic? And give the reasons for your choice. So let's go back. All they are asking is if the reaction is endo or exo. So let's look at these two. It says that if you raise the temperature, the reaction is almost colorless. So which means it looks like exo. Exactly. If you have a reaction, A plus B is C plus heat, right? So this reaction is exo. You can try with both and you will realize. If the reaction that we are studying is exo, when we add heat, all the exothermic reaction will shift the equilibrium to the left, to the products. And in this case, it does, because it is almost colorless. So that's what you have to explain. And then you will have to do exactly the same for a different system. So you will have a different reaction. You have this reaction that when it's dissolved in alcohol has a blue color. And when you add water, has a pink color. So all you have to do, basically, is that you have the control here, the color. And then you're going to look at, okay, what happens if I add hydrochloric acid? It says blue. Who is blue? The reactants. And then you're just based on the color, you know the reactant is blue and you know the product is pink. And based on that, you will answer your questions. And then the last part is going to be exactly the same as what we did. You are going to see if when you add reactant, it makes the Q bigger, and if Q is bigger than K, what happens if it shifts to the products or shifts to the reactants. So I think I will stop here the recording, and I hope this was helpful, but I will stay as much as you need to answer questions. And thank you everybody for being here.